people from all walks of life to meet in a multidisciplinary program so as to create mutual awareness and hopefully to find some creative solutions to solve problems and achieve peace at all levels, from peace within ourselves to peace within nations, cultures, and religions. It is also my great pleasure on behalf of Chulalongkorn University community to welcome our esteemed speaker, Professor Riccardo Giacconi, 2002 Nobel Laureate for Physics, who will shed light on the development of X-ray astronomy. Today, we relished the unique opportunity to meet the physicist who has constructed X-ray telescopes and who has laid the foundations of modern X-ray astronomy. We are delighted to have with us today fellow members of the Science Circle, educators from multidisciplinary backgrounds, and as well as enthusiastic audience, to learn from the expertise and insight of a person whose contributions have increased our understanding of the sun, stars, and galaxies, and have provided us with a new knowledge that has changed the way we look upon the universe. I would like to take this opportunity to express my sincere appreciation to the International Peace Foundation and to Kasikorn Bank, who helped in making this wonderful series possible. Once again, may I thank our distinguished speaker for traveling halfway around the world and for giving us his time. Thank you very much.
Thank you, Professor Dr. Kunying Suchada, the President of Chulalongkorn University. Next, may I invite Mr. Uwe Morawetz, Chairman of the Board, the International Peace Foundation, to give his remarks. Mr. Uwe.
As a contribution to the Decade for a Culture of Peace and Nonviolence, initiated by the United Nations General Assembly, Thailand has been chosen as the host country for the event series Bridges, Dialogues Towards a Culture of Peace, initiated by the International Peace Foundation, a non-political independent foundation under the common patronage of 21 Nobel Peace Prize laureates based in Vienna. Between November 2003 and April 2004, already more than 100 events took place with 10 Nobel laureates, as well as with other keynote speakers such as Reverend Jesse Jackson and artists like Jesse Norman, who all came to Thailand without any fee to support and promote the kingdom as a center for dialogue and international understanding. Her Royal Highness Princess Mahachakri Sirindorn graciously presided over several events, which in total reached an audience of 30,000 participants, including different target groups, thanks to a variety of partners, ranging from major universities and ministries to the Royal Thai Army, NGOs, businesses, media, and the diplomatic corps, which hosted the events in cooperation with the International Peace Foundation. The pluralistic program of Bridges highlights the International Peace Foundation's intercultural and transdisciplinary approach towards peace. The Foundation doesn't take sides, but acts as a mediator by creating an independent platform for dialogue where representatives of science, politics, economy, culture, religion, the media, and youth can meet, share their viewpoints, listen to each other, and find mutual ways of understanding and cooperation. สันติไม่อาจสร้างขึ้นได้ในเวลาอันสั้นแต่เป็นกระบวนการที่ต้องอาศัยเวลามูลนิธิจึงไม่ได้จัดกิจกรรมสารสัมพันธ์สู่สันติวัฒนธรรมเพียงเพียงครั้งเดียวแต่เชิญผู้ได้รับรางวัลโนเบลและผู้นำของโลกร่วมกันสร้างสะพานเชื่อมสันติกับผู้นำของไทยจากทุกสาขาและประชาชนทั่วไปอย่างต่อเนื่องทั้งนี้ผู้ได้รับรางวัลโนเบลและปาฐกที่มาร่วมงานนี้ได้ให้คำสัญญาแล้วว่าแม้จะสิ้นสุดโครงการท่านจะกลับมายังประเทศไทยเป็นประจำ เพื่อที่จะรักษาและกระชับความสัมพันธ์กับสถาบันต่างๆและกับประเทศไทยให้ยั่งยืนมั่นคงต่อไปในโอกาสนี้ผมขอขอบคุณศาสตราจารย์คุณหญิงสุชาดาคีรนันนาอธิการบดีจุฬาลงกรณ์มหาวิทยาลัยธนาคารกสิกรไทยตลอดจนพันธมิตรและผู้ให้การสนับสนุนทุกรายที่ได้ให้ความร่วมมือเป็นอย่างดียิ่งเสมอมา I'm especially grateful to Professor Riccardo Giacconi, who came to Thailand without any honorarium to support our efforts, and I now look forward to his keynote speech and to his important contribution to build bridges. ขอบคุณมากครับ
Thank you, Mr. Morawetz, Chairman of the Board, the International Peace Foundation. And finally, may I now request the honor of Ms. Janjari Buranawait, the first Vice President, Corporate Communications and Administration Department from Kasikon Bank, our major supporter, to give an address.
Good afternoon, President of Chulalongkorn University, Professor Kun Ying Suchada Kiranan, Chairman of the Board of Directors of International Peace Foundation, distinguished guests. In celebration of humanity without borders and admirations of Thailand as a peaceful country, Kasikon Bank is proud to sponsor speeches by 18 Nobel laureates for the next 5 months. Each Nobel laureate will deliver his or her keynote addresses at various universities all over the country. As part of the International Peace Foundation, Bridges Dialogues Towards a Culture of Peace project. On behalf of Kasikon Bank, I am honored to present Professor Riccardo Giacconi, Nobel laureate for Physics in 2002. Thank you very much.
Ladies and gentlemen, before we begin, I would like to take this opportunity to introduce our speaker. As it is known around the world that 2005 is the World Year of Physics, it is very appropriate that we start Bridges, the dialogue towards the culture of peace, with a series with Professor Riccardo Giacconi, the 2002 Nobel laureate in physics. He is a research professor at Johns Hopkins University, Baltimore, and the president of Associated University, Washington, D.C. Professor Giacconi was born in Genoa, Italy, and spent most of his early years in Milan, where he obtained a PhD in 1954. He then came to the United States on a Fulbright fellowship to work as a researcher at Indiana University. In the consecutive years, he worked in leading posts at, to name a few, the American Science and Engineering, Harvard University, and as the first director of the Space Telescope Science Institute at Johns Hopkins University. With his experience as principal investigator of several earlier NASA programs, he planned and executed the science operation of the famous Hubble Space Telescope. Professor Giacconi's achievement in X-ray astronomy has earned him many prestigious awards from renowned institutions around the world, including Helen B. Warner Award of the American Astronomical Society in 1966, the Como Prize of the Italian Physical Society in 1967, Roentgen Prize in Astrophysics in 1971, many distinguished awards from NASA, the Wolf Prize in Physics in 1987, and the list continues. And Professor Giacconi was awarded the greatest prize, the Nobel Prize in Physics, in 2002 for his pioneering contributions to astrophysics, which have led to the discovery of cosmic X-ray sources. Professor Giacconi's contribution laid the foundation of X-ray astronomy and provided us with a new knowledge that has an outstanding and marvelous new view of the universe. Ladies and gentlemen, without further ado, please welcome Professor Giacconi.
Good afternoon, the President, academic authorities, dear colleagues, students, ladies and gentlemen. It's a great honor for me to give this lecture, which has been made possible by the International Foundation for Peace, and particularly now in the wake of the problems which have occurred with tsunami. I thought that I should not come, or that I wanted to know whether you wanted me here, and I was assured that science goes on, progress goes on, and we are still trying to build bridges, and this is why I'm here. I prepare my lecture in the following way. I don't wish to discuss things which I don't know personally, and I thought I might contribute in three areas. The first one was science itself, basic science, X-ray astronomy, which is the area in which I'm strong as a scientist. The second one was to try to discuss with you the relationship between basic and applied science. And I hold fairly strong views on that, which may not be common here or in Europe. That is that basic and applied science are very closely intertwined and almost undistinguishable in today's world. And finally, I have had some experience in putting together large research programs, and I've been asked to discuss this with some of the people here in Thailand, which are most interested in that. Well, of course, today I cannot cover all of three subjects, so I will start off with basic science. What I will try to do, and the objective of this talk, is not so much to teach you about X-ray astronomy, because I expect you to become X-ray astronomers, but to perhaps emphasize how interesting and exciting and stimulating basic science can be, and what are its relationship then to applied applications. So what I will try to do is to describe to you some of the initial steps, at least, and some of the current things which are going on in X-ray astronomy, and more or less from the point of view of a young man, which I was, in 1959, when I was first given the task to initiate a program of space research at a very small private research company. And what I should say about that as an introductory remarks is that as a result of World War II, lots of technology was developed, including rockets, which, as you know, devastated London and so forth. After the Allied victory in World War II, some of these rockets were brought back to the United States. And scientists started using them for research. This research opened up a whole new world, because by going outside the Earth's atmosphere, you can now observe the stars as they shine in their own light. Light which actually cannot penetrate the atmosphere and come to the ground. So in a sense, X-ray astronomy is a brand new type of astronomy that just could not be done before the space program was developed. So in 1957, the first Sputnik went up. Tremendous desire existed in the United States to catch up with the Russians, which were considered to be a deadly threat, and it was impossible to let them go ahead in technology, so there was ample funding. And this small corporation gave the opportunity then to start new disciplines and new research. And what happened is that an old mentor of mine, Bruno Rossi, a very distinguished scientist in his own right, professor at MIT, was associated with this little research corporation, and suggested that perhaps among the other things that I was looking for to do in space science, I should think about X-ray astronomy. And this was something which actually was discussed at very high level of scientific counseling to which I obviously had no access being a young man. And it turned out that I was, because of my previous work, for thesis work, which was not in astronomy at all, was elementary particle physics, I was well qualified to start this thing. What I would like you to take is the perspective of what we were doing as a detective story. So I'll start from zero, I'll go through the first detections, and then I'll say what followed later and how we try to understand what we were seeing. So the first slide is, I have to do it. So the first slide is just a calculation. Don't try to read all of the numbers. It's X-rays have been observed to come from the sun. They constitute a tiny fraction of the total light that comes from the sun. And by X-rays, by the way, just so that we understand each other, it's the X-rays that are used for medical research or for dentistry or whatever. Those are the type of X-rays that we are thinking about. So a very tiny fraction of the light from the sun comes in X-rays. It's enough, though, that when there are variations on the sun, it creates problems in the ionosphere, and that is what causes communication difficulties. When you try to look at other stars, and that's what that table is trying to do, they are so far away that if they emitted at the same amount that the sun does, you could not see them by a factor of 1,000,000. So the problem that I was given, so to speak, was to try to figure out how I could observe objects in the sky, stars, which would give at my detectors on Earth a flux 1,000,000 times smaller than what had been seen before. And by looking at the work which had been done before, I noticed that some technologies to which I was familiar with were used to reject, for instance, cosmic rays, which are particles that come from the outside, to improve the sensitivity of the detectors, and even to design the experiments better, had not been used. And so we designed an experiment which was very simple. This thing that you see there is the instrumentation that stayed inside a nose cone of a rocket, about as tall as I am, that rack is, and it has detectors which were pointing out on the outside. Doors were open as the rocket went up, and then as it was up in altitude, you would try to scan the sky, to look around the sky to find out X-ray sources. And that's a representation of how the rocket, the nose cone of the rocket would look like and how it would scan the sky. Now, the expectation as we launched this was that we would see either nothing or the moon, perhaps, by reflection of the X-rays from the sun back to us, but very, very faintly. What we saw instead was the signal which is shown here, which is simply the sum of all of the time that the rockets stay above the atmosphere, about 300 seconds, that's 5 minutes, and collecting counts from different parts of the sky. And as you see, there is this tremendous bump in the middle, which we didn't expect at all. And then there is a kind of a background there, which also was unexpected. So what is plotted there is the number of counts we received versus the position in the sky that we were scanning. As soon as this discovery was made, then it became very, very exciting to go on. Why? Because in the direction in which we were seeing this tremendous peak of radiation, there was no correspondingly luminous object. And therefore, it meant that this object that was emitting these X-rays was very different from our own sun. Also, the total amount of energy that was coming out was great. It turned out later on, we found out it was 1,000 times the sun at all of the wavelengths. And so in this first rocket shot, we found an object which was very different from the sun, very hot, emitting in X-rays, and in which the proportion of X-rays versus normal light was very great. There is no process known on Earth where you can produce X-rays that efficiently. For instance, when you go to the doctor and he gives you X-ray scans, he is producing 1,000 times more heat than he's producing X-rays. And the same is true for the sun. So this is a very strange physical process which is going on. And the other process which was found was this uniform background. This is the laser pointer, I'll take it. Yes. No? Yes? I'll do without, I think. Okay. That was coming from everywhere. So this was done in June 1962. And, okay, thank you. Fine. Uh-oh. Yeah, I see it. Okay, good. And since then, it's fair to say that it took about 10 years to explain what this bump was. Oh, I can't see it. So small, it's my eyes that are playing tricks, or I can't see the spot when I do it. So it took 10 years to explain the big bump, and about 40 years to explain the overall diffuse background. So without going through all of the steps, because I don't think that's important to what I want to leave you with, I'll now jump to 10 years, from 62 to 70, and go to the satellite experiments which we first undertook. A rocket only gives you about 5 minutes above 100 kilometers. So you can observe the sky in X-rays for only about 5 minutes. The total amount of the number of rockets that had been launched in the 10 years going to 1970 was something like a dozen, 12. So altogether, the entire sky had been observed only for an hour. As soon as you place a satellite in orbit, you can observe for 4 years. And therefore, you have tremendous greater sensitivity and ability to follow what is going on with the particular sources. The satellites scanned the sky repeatedly, and over a number of years, found something like 360 of these sources. And some of them are, let's see, what is shown here. Here we go. What is shown here, what are these coordinates? This is the galaxy. This is the plane of our galaxy. This is galactic coordinates. So all of the objects which are along here are stars in the spiral arms of our galaxy. And the objects which are shown up here instead are outside of our galaxy. So there is about 360 of them. Some of them are very interesting. For instance, the ones which are marked Coma here, Perseus. These are not single galaxies, but ensemble of groups of maybe 1,000 galaxies. And what we found with respect to these groups, and I won't go back to them at all, is that in fact these groups, which are made of these 1,000 galaxies, in the space between them are filled with extremely high temperature gas at 1 million of degrees. And this gas is what we are observing in X-rays. Now this gas is very thin, very tenuous, low density. However, the spaces are so enormous that more matter is contained in this hot gas than in all the galaxies and all the stars put together. So already this particular finding, just this, increased the mass, the normal mass that we knew existed in the universe by a factor of 10. And this mass had gone not detected, unperceived by any of the means we had until we actually got to X-ray observation. So this was one finding. All of the rest of the objects that you see here are active galaxies, galaxies in which the nucleus is particularly bright. And the object that you see along this line, were still mysterious in 1970. SCO X1, the very first source that we observed, was this one here. It's shown with a big dot to show that it's very bright, and the other ones are correspondingly smaller dots, means weaker and weaker. So now I will concentrate about how did we use this satellite to find out what this source, and actually many of the others, are. So I will just jump that. Okay, here is the scan to show you visually what the satellite sees as it scans through the sky. So it sees a background. This is number of counts as the satellite rotates. Then a very strong source, the same one that we saw the first time. Now notice how much better is distinguished from the rest, because of better instrumentation. And then it keeps going and until you made a complete scan. Now we had a particular capability on this satellite which we used to great effect. Here the satellite was scanning the sky, was rotating very slowly. We could go slower yet, or faster. When we go very, very slow, what we are doing is we are lingering, we are staying on the source for a long time, so we can see if it varies. And what happened was that we observed the source, this is a source in Centaurus, which was pulsating. The triangular shape is due to the fact that you're looking like through blinds, Venetian blinds or something. And so it defines the field of view. The pulsations that you see inside there are due to the source. The source is switching on and off very fast in 2 seconds. Now this is a star which is changing its emission in 2 seconds. It's just as if you looked at the sun and the sun was pulsating on and off. Now, next thing we tried to find out what was happening to these pulsations. And here are the data which show, and they are made in points because the precision of the measurements is such that you couldn't show the errors. So what you see is that the data on this pulsation define a periodic function, sinusoid. And we are very familiar with sinusoid. We are familiar with that in electricity, and we are familiar with that in Doppler system. That is, you all know about the Doppler effect. The train is coming towards you, pitch is high, the train goes away from you, pitch is low. And this is what is actually happening, that the period of pulsation is becoming shorter and longer as something else is happening. And what else is happening is shown here, where the intensity of the source is shown. These are days now. And what you see is that you have a null of the change in pulsation period here and here when the source is either behind a star or in front of it. And so the picture that comes out is very simple now. It's a source here, which is an X-ray source, a star presumably, which is going around a companion. And you see the eclipse. This is why the changes in intensity. And you see the sinusoidal variation of the period because of Doppler effect. Now, maybe at this point we thought we have explained everything there is to explain. In 1967, that is 5 years before these measurements were done, pulsars were found. That is, stars which are pulsating in radial. This was the first discovery of the pulsars. And there is a property of these objects that they are turning the speed of rotation of a star in pulsations. And so as they pulse away, they must use up energy, and they are slowing down in their rotation. So to confirm, one possible explanation of what we were seeing was, here is a pulsar, which is emitting in X-rays, that's okay, and which goes around the other star. And so if we measure the period of pulsation very precisely, we should see this period of rotation slowing down. This object is losing energy. So we measure for 4 years. I don't know how to go back now. Well, that's all. How do I go back? Yeah, that's it. We measured the period of pulsation of this object for 4 years. Here are the years, here's the period of pulsation. And what you find is that it's becoming faster and faster. The rotation is becoming faster and faster. So this object is not losing energy, it's acquiring energy. Now that was a phenomenon that had not been observed before. And so finally the explanation of all of this was the following. Now what you're seeing depicted here is a cut through the gravitational potential, equipotential surfaces, but I want you to focus on this picture. What it shows that a possible mechanism for energy emission by this source is the fact that gas from one star is falling onto the other one. And as it falls, it acquires energy. It turns out that if you have a star which is very dense, like a neutron star or a black hole, then the energy which is acquired by this matter falling on this very collapsed object is of order of 100 times more than you could generate by nuclear fusion. So it's an enormous amount of energy. And this has become the standard explanation now for all of the binary systems which are seen to emit in X-rays, but also more generally for the emission from the center of galactic nuclei, which are very massive, maybe 1 million or 100 million solar masses, and in which the emission, which is greater than all the rest of the galaxy combined, is due to this, which is called gravitational infall of matter. Now, we found two types of this binary system. One, which is depicted here, in which you see the gas from, this is of course is an artist's conception, the gas going from the primary, falling on the secondary, it's very hot, so it's conductive and it can only fall on the magnetic poles. And then another type, which is this one, Cygnus X1, where the matter is falling forever on something from a surface from which light cannot escape. This was the first detection of a black hole of solar masses. A black hole is a body which, you hear the names and it's popular because it seems like black magic, but it isn't. It simply means it's an object, a star, which is so dense and so heavy that no currently known physical law can maintain its surface. And therefore, at the moment, we think that what happens is that the material in the star will fall down forever. So this was the solution, if you wish, of the first detective story. What was this object that we were seeing? It is one of these binary systems. The material is heated by infalling on a very deep potential well, and it's very effective for it to emit everything in X-rays. That's why this tremendous X-ray emission. Something that should be said is that it's not immediately obvious, is this process is not something very strange. It's something that happens in most stars, because most stars are in binary systems, and one will start off bigger than the other. By evolution, it will go through its life and then no longer be able to generate heat from inside, which is what keeps it puffed up to a given radius. Therefore, it will collapse. And the companion star will start putting gas onto this companion until finally this one will continue on until it evolves to the point that it cannot support this surface, and then it will collapse and we will end up with two collapsed objects. This is generally what happens to binary stellar systems. Now I want to turn to a completely different subject, if you wish, because it's necessary for me in order to explain to you how we solve the second problem. And I will go much faster on this because I think time is running on. But let me just say what happened. What happened was that when I was a graduate student, I did a thesis in cosmic rays. And I was up on a hut at the foot of the Matterhorn at 3,500 meters, which is not terribly good to live at. And I had to collect these particles that were coming on this instrument I had. And it took me 2 years to receive 80 events, 80. That was just barely enough statistics to be able to confront this with the theory that had been developed by Fermi. But I told myself, never in my life do I again want to be involved in a project where the statistic is so low, because this takes too long. I mean, I'm going to be dead and gone before I can finish. So when I first started thinking about X-ray astronomy, I concluded that there were so few X-rays that it would be very difficult to do something very important. It turned out that we were extremely lucky with the first rocket because there were these unusual objects. But there is the desire to look at normal stars or very distant objects in X-rays. The only way that you can do that is just like you do in visible light, that is to have a telescope. However, if you want to use a telescope, it means is some means of focusing your radiation from a large area into a small detector. If you put X-rays on a mirror at the normal shape, they just penetrate the mirrors and are lost. However, it turns out that the peculiar index of refraction in matter is negative. And therefore, you have a phenomenon which is called total external reflection that is bouncing off of light waves, X-rays, from mirrors, provided they hit the mirror at very shallow incidence. So that's the principle. So actually, I wrote an article on this as I started because I wanted to have some assurance that ultimately I could do X-ray astronomy no matter how difficult it would be. And it was clear that by using such a telescope, you could have gains of maybe more than 1 million. However, technology was very difficult. And so it was a blessing that X-ray astronomy could go ahead while we didn't have this telescope. We developed it in around 1970, and the first application, these are different models and so forth, the first application was the sun because it was the easiest target. And I show you this to show you, this was obtained in 1973 from the Skylab, which was one of the first space stations, so to speak. The astronaut went up, took the film cassette and changed it and brought it back to Earth. But also to show how different the sun looks in X-rays from what it looks like in visible light. From the visible light, you are seeing the chromosphere, which is at about 6,000 degrees. In X-rays, you see millions of degrees, but they are hot plasma, which is contained by the magnetic field. So what you are seeing, essentially, is a map of the magnetic field of the sun. This was easy because the sun puts out a lot of X-rays because it's very close to us. But when we want to use it for distant stars, it took longer, and let me just go through fast. And it took 2 generations of spacecraft to come to the one we have currently up today. This is called Chandra, in honor of the great physicist, Indian physicist Chandrasekhar. And Chandra is, maybe he wouldn't have liked it. I mean, he was a very serious person. He didn't like nicknames, but that's what NASA called it. This is a very large telescope. Its cost was also very large, about $1 billion. The size is about the size of a truck. It's about 10 meters from here to here. And it has given us a sensitivity and an angular resolution which was impossible to obtain without telescopes. And so I'll show you some of the pictures which have been taken, some very dramatic. For instance, here you see a picture which is obtained by superimposing many pictures taken over a period of 2 years, actually. And what you are seeing is, to the right is the picture taken in visible light by the Hubble Space Telescope, and to the left, the picture taken by Chandra in X-rays. And what you were seeing, what you were looking at, is I'll try, if you wish, maybe I'll do it once again. What you are seeing, I don't know if I can go back now. I may have fouled up everything. No, here we go. What you are seeing is a pulsar in the middle, with the pulse coming out at both ends, and shock waves of magnetic fields and plasma, which are radiating from this neutron star. This is just the noticeable thing here is that the visible light picture, with the best telescope, the visible light that has been built in visible light, and the picture in X-rays are giving you essentially the same angular resolution. So the field has improved tremendously over the last 40 years. Moreover, these two different wavelengths give you an idea of the physical condition of the gas, of the temperature of the gas, and the physical processes that take place within it. Now, to give you another example, again from Chandra, here you see this, I'm sorry. What you were seeing before was the supernova Crab Nebula, a solar mass type object, a star, which is in our own galaxy. This is an extragalactic object, and you see a very similar phenomenon. There will be shock waves around here, a galaxy, an accretion of matter from a galaxy, and a jet of matter being projected outside. Now, I concentrated, I must say, my interest on finding out the reason why we were seeing this uniform background coming from extragalactic sources. And so this was a pointing of 1,000,000 seconds, that's 10 days, of this Chandra satellite. It was very difficult to convince my colleagues to give me that much time. And in a region of the sky where nothing was known before, the size of this region, to give you an idea, is about this size would be the full moon. Okay, so it's fairly small. And there were some 300 sources in there. What are these sources? These sources are galaxies very, very far away from us, and which are dominated by the central emission from a supermassive black hole, maybe 100 million solar masses, and of which we observe a very large number. And the reason why this uniform background seemed to be uniform is because these many sources could not be distinguished one from the other, and apparently they looked continuous, although you see they are discrete. We found out that okay, well, wait a minute. So, in a nutshell, this exposure, this picture that we took was taken at the very lowest energy intensity that we could get it at. And here you see the first discovery, then the satellite, some other satellites, and finally where we are today. And from the intensity here to the intensity here, there is 1 billion times. So what happened in X-ray astronomy, we have increased our sensitivity by 1 billion times since we started, last 40 years. And if you think about what the same kind of graph would look like in visible light, if you have a naked eye to the Mount Palomar and then the Keck telescope, it's also 1 billion times. Keck telescope sees 1 billion times further, if you wish, than the naked eye. So there was a tremendous increase in sensitivity. Let's see. Well, this is too detailed. Okay. We then, once we had these objects, we then use, and I show you this not because I want you to understand all of the details, but to tell you how astronomy is done today. This is Hubble, the Hubble Space Telescope, pointed to the same sources we have seen in X-rays. And the contours here are the X-ray contours, and as you see, every time we see some source, there it is, there is a visible light object. and that is why we can measure the distance and we can measure the type of object. Sometimes the objects are so distant that Hubble, which is the best telescope we currently have, cannot see it at all. For instance, here is a contour map of the X-rays, and there should be a source in there. We're seen with Hubble. Hubble doesn't see it. That is that in some areas, the capability in X-ray astronomy have exceeded the capability of observing objects in visible light. So we go to the next telescope, which has been sent up, which is up currently, Spitzer it's called, and it observed the sky in infrared. And in infrared, you see the source that was observed in X-rays. Now, why is that? Because there is a lot of dust around. The X-rays penetrate the dust, and so do the infrared, but not the visible light. I hope to make one point. One is that you do astronomy these days by using all of the wavelengths of the electromagnetic spectrum because they give you different information about the object you are studying. And also somehow that a lot of the matter of the universe and a lot of the phenomena that go on are not apparent to us without instruments. So it's not like they were made for us to be seen. They are there because those are the natural events that go there. And if you work hard, then you can get to see them. They don't care about whether we are here to observe them or not. They continue. I'll go on with the, okay. This is a picture of the same region I showed you before, but taken over a 2-year period of time. This just got stuck or something, or it was supposed to. Let me try to see if I can get it back. If you look at them carefully, you see that all of these things are changing in intensity. There it is, moving along very, very slowly. I think we are still fairly slow with this computer. And only, well, this is jumping. If you look at those sources, you see them pulsating. What is it? Well, these are 10 observations of a day each in which we look at these very, very distant sources. And what is happening is you see them changing in intensity by large factors. And this fact is due to the fact that the central region of the galaxies is quite small. It's very compact. I wanted to show one more thing because I wanted to make sure that you understand that I've given you a story from my point of view, my personal involvement and point of view. But X-ray astronomy is much bigger than any one man. And we couldn't have made this progress if it had been one person. To give you an idea of what we are talking about, when one is talking about $1 billion, that is 10,000 man-years of effort. So 100 men for 100 years could do it. That's about what it takes to build a temple. So it's a large effort, and a lot of people are involved. That's one point I wanted to make. The second point is that many, many nations have now joined. I mean, it's usual for you to look at all of the little names, but I will point out, I don't know, let's see, Exosat, European, Ariel, English, Akucho, Japanese, Italian, Astro D, Japanese again, Spectrum X, Russian, and so forth. So that the whole world has joined in this research. And I will conclude with a few remarks which I wrote down because I wanted to make sure that I remember. I mean, I know the rest of the stuff fairly well, but this one. So what have we learned? All of this effort, all of this money, what have we learned? What we have learned is that there are the existence of states of matter previously speculated on but not known to us. That we have seen new forms of energy production and release in the cosmos. The fact that most of the ordinary matter in the cosmos is too hot for us to see. But even more fundamentally, the importance of explosive events, events which occur with very high energy, very high temperature involved, for the evolution and dynamic of the universe. The universe is not quite this kind, gentle place where things evolve very, very slowly on eons and millions of years and billions of years. Things occur on the scale of seconds or milliseconds, abrupt, violent explosions. And the changes that we saw were due to that. And finally, I think, and I will go into some of this tomorrow, I think, is we have learned techniques which have proven of great use in medicine and may prove of great use for the diagnostics and the development of new forms of energy. Now, I don't mean that I want to justify the research we did on the basis of the results that we have taken. I think the research we did was justified by the beauty and interest and the intellectual advances that we have made. But a necessary consequence and concomitant effect is that you can't do this research without developing very high technology, which then comes back and hopefully will be of benefit to mankind. Well, thank you for your attention.
Okay, thank you very much, Professor Giacconi. Now I think many of the audience may have some questions to ask you. I think the best way to do this is we allow the audience to write a question on a piece of paper, and then I'll pass it on to you. สำหรับท่านผู้ฟังนะครับถ้าใครมีคำถามนะเขียนใส่กระดาษที่แจกเอาเวลาล่วงหน้านะครับแล้วส่งขึ้นมาข้างบนได้เลยนะฮะเขียนเป็นภาษาไทยก็ได้นะครับเดี๋ยวผมจะแปลให้ครับมีเวลาประมาณ 10-15 นาทีนะครับ Anyway, I'll start with the first question then while we wait for that. I think as it is a year of physics, a world year of physics 2005, what do you consider as the most ambitious goal of your future research?
In astronomy?
In astronomy, yes.
Well, I think that the matter which is of greatest interest to astronomers and astrophysicists today is as follows. I mentioned to you that in these groups of galaxies, we found that most of the matter that was contained in the group was not in the visible stars and galaxies. And in fact, how we conclude that? Well, we saw the X-ray emission from the gas. We could measure that mass. That mass turned out to be something like 5 times the mass in the galaxies and stars. However, even that mass, augmented by the one in X-ray, seen in X-rays, would not be enough to keep the cluster together. There has to be more mass hidden in the cluster that keeps the galaxy from flying away. And that we have called dark matter. That is matter which we can't see. And about 30% of the mass in the universe, we now believe, is contained in this dark matter. Could be neutrinos, could be whatever. Now, most recently, though, what we have found is not only the baryon mass, which is the mass of normal matter, was not enough to explain what we were seeing, so we had to invoke this dark matter. But the universe does not behave as if that was the only matter present. What we have observed is the universe contains another form of matter of which we understand nothing, I mean, just to make it simple, which acts as a repulsive force, so that the universe does not start with a certain matter, expands, and then fall upon itself as we anticipated. The universe passes through phases in which it expands, then the speed of expansion is reduced, okay? And then finally it expands again. And this repulsive force we call dark energy. It was foreseen in Einstein equations, although he didn't believe in it, but it was there if you wanted to find it. And we understand nothing at all about it. So basically what I'm saying to you is we understand only 5% of all the matter contained in the universe. We think the explanation for another 25% is not too strange or too fantastic, but for 70% we have no explanation whatsoever. Now that is the most interesting thing that could have happened to us, the fact that we don't understand anything. I mean, with all of this work and so forth. So it means new theories, it means new finding, it means a wonderful opportunity for young people. I mean, maybe somebody in the audience here will find out what it is. I certainly won't be able to, I think, in my lifetime. So that's perhaps the most interesting project that we have in astrophysics today. The other one is more, more reasonable, is to explain how come from the initial explosion, where everything was chaotic and mixed together, we come to the structures as we see today. What was the actual process whereby stars were formed, galaxies were formed, elements, planets, life perhaps, to explain what's around us today.
Okay, thank you. So I think we have for the future physicists and astronomy
Yes.
people, that's an assignment for them to do in the future,
Yes.
right? Okay, this is a question related to the peace aspect, maybe, or general
Peace.
aspect. Yes. It's actually, you talk about your first rocket flight with the X-ray detector. Was your first rocket flight with the X-ray detectors purely for the basic research?
Yes.
Or is there any other applied, any other agenda attached?
The answer is yes, although it gives an interesting prospect of how research is supported in the United States. I went to NASA and made to them the proposal to fly rockets to see X-ray stars. And the answer was, since there were no X-ray stars, why did I want any money? So that was a little disappointing. So then I went to the Air Force. And the Air Force at that time, of the United States, at that time hoped to have some role to play in the exploration of the moon. And I convinced them that maybe I could look to X-rays bouncing off from the sun onto the moon and measure the composition of the lunar dust. It turns out that the sensitivity wasn't there. We ultimately have measured X-rays from the moon, and they even have been used. But by that time, the Air Force had lost any interest in getting involved. Actually, they were told not to get involved. And NASA took the leadership in exploring the moon. But maybe that's some of the confusion. The point is that there are many separate sources of funding in the United States, thank God. And if one agency tells you no, you can go begging at some other agency and say, please let me start. And you have to invent some idea on what you tell them and why they might be interested. So but no, there was no military involvement into that. I have been involved in classified work for my country, and particularly at the time when Kennedy was trying to negotiate a nuclear test ban treaty. And before that was done in '62, there were some atmospheric nuclear weapon tests in which I participated with my group to measure the X-rays that were coming from these things. And that's about it.
Okay, so I think that's, that answer leads to this question, is that the discovering of the X-ray astronomy techniques, and can it be led into other applications, such as the medical applications or industrial applications?
Well, I will go through tomorrow, I think, when I talk about relationship between basic and applied science. But let me just say, I'll give you a very short summary. By finding techniques in which you could measure very small quantities of X-rays, we hit upon some way to do X-rays of persons and things with very, very low dose. And the first application of that was in airport baggage inspection systems, which now are all over the world. These are different from the kind of X-rays you get at when you go to a doctor, which puts you between an X-ray source and a plate, because that system is very inefficient. So, for instance, you couldn't really do X-rays of pregnant women. It would be damaging the fetus. On the other hand, if you have an X-ray beam which is scanning, then this becomes, on a detector behind it, this becomes a very effective way to measure the matter which comes in between. And that's why airport inspection techniques have become so prevalent. They don't even damage film because the dose is very, very small. So that was one initial application, and essentially a derivative of that, which we did not do. My group did not do. I want to make it very clear. We actually were still working on the mathematics, and we didn't reach the conclusion that the person who developed the CAT scan, who then got a Nobel Prize for it, did conclude. I mean, and the point is that this is the same technology whereby you have a number of detectors around a circle, and that by solving the fairly complicated differential equations that describe what's going on, you can make a scan of a person with very low doses, again, particularly the brain and so forth. So those were the other applications. The third thing that I had in mind is that the temperature of the bodies that we are studying is the same temperature you would obtain, if you can, way to do X-rays of persons and things with very, very low dose. And the first application of that was in airport baggage inspection systems, which now are all over the world. These are different from the kind of X-rays you get at when you go to a doctor, which puts you between an X-ray source and a plate, because that system is very inefficient. So, for instance, you couldn't really do X-rays of pregnant women. It would be damaging the fetus. On the other hand, if you have an X-ray beam which is scanning, then this becomes, on a detector behind it, this becomes a very effective way to measure the matter which comes in between. And that's why airport inspection techniques have become so prevalent. They don't even damage film because the dose is very, very small. So that was one initial application, and essentially a derivative of that, which we did not do. My group did not do. I want to make it very clear. We actually were still working on the mathematics, and we didn't reach the conclusion that the person who developed the CAT scan, who then got a Nobel Prize for it, did conclude. I mean, and the point is that this is the same technology whereby you have a number of detectors around a circle, and that by solving the fairly complicated differential equations that describe what's going on, you can make a scan of a person with very low doses, again, particularly the brain and so forth. So those were the other applications. The third thing that I had in mind is that the temperature of the bodies that we are studying is the same temperature you would obtain, if you can, in nuclear fusion research. So when we talk about doing burning hydrogen, in other words, and having a source of energy without uranium problems, byproduct, etc., which is fusion rather than fission. The source that you would obtain is at a several million degrees temperature, and so if you want to see what's going on in the fusion reactor, you take an X-ray telescope such as the one that I've shown you, and you take a picture of it, or you take spectra of it, and so forth. So it will be useful for diagnostic and possibly for the development of new forms of energy.
Yes.
Okay?
Thank you. I think my plasma student would understand that, because I just gave a lecture to them.
That's it?
On that as well. Yeah, on the
Good.
it's plasma fusion. So the diagnostic is the X-ray detector. It's one of the diagnostics.
Yes.
Okay. That's another question actually from the students, actually physics students. I think his interest is in the black hole.
Yeah.
And he was wondering, the use of X-ray astronomy can yield useful information about the black hole? In what way?
Okay. First of all, let me again make sure that we understand each other when we talk about black holes. I am an experimentalist, okay, so I don't believe in angels or anything. And my definition of black hole is very simple. It is a body which has a definite radius, and within that radius there is contained so much mass that light cannot escape it. Now, the reason why I'm being precise is because I don't know what is inside that radius. It could be that it is a singularity, meaning that the material keeps falling forever. That would be a frozen singularity. It could be there is some other form of matter that we know nothing about. We from the outside cannot receive information from the inside through light. So we cannot yet say anything about what's there. Now, what we have observed in X-rays, though, is that gas is attempting to fall onto this black hole, and we have seen this in these giant supermassive black holes. And as the gas is traveling toward the black hole, the radiation that it emits, for instance, if there is iron in this gas, is very characteristic. It has a particular wavelength. And as the gas is falling into the black hole, you see the radiation wavelength shift because of gravitational redshift. So we are actually learning things like the rotation of the black hole, the size of the black hole, and so forth, by looking at X-ray emission. And this has been done with two spacecraft. One is Chandra, and one is, which are orbiting right now. This is very recent research. And the other one is XMM, which is the European X-ray multi-mirror mission, called Newton, I believe. Okay?
Okay. So I think to our last two questions on a
Yes?
general matter, I think a lot of students has wrote this question. To inspire young children, or actually researcher, physics researcher, could you please share with us some of your key strategies which have made you successful as a researcher? What is your key strategy?
I have two daughters, neither one of which wanted to take research because they consider it's too hard, and they both took banking as being a more profitable and research. So obviously, as a father, I wasn't too successful in inspiring people to do research. I think research is, at the moment, it's not terribly, it's very hard. There is a lot of drudgery, and few people have the privilege and the joy of the kind of discoveries I've been describing today. So I feel I have lived a really privileged life. However, even if you have to go through a lot of drudgery, I think that what is true is that nature is very bountiful. If you work hard enough, there is a beauty and an order hidden in all of this apparent chaos, which is wonderful to behold. And so that's why I would say that perhaps to a scientist, the most intriguing part is this hidden harmonies, laws, rules, which have a beauty of their own. Then the fact that we always say that we do research in order to benefit mankind, we always say that, but actually we do it to benefit ourselves, for our own pleasure, just as if a painter, paints. And he says, but how come, what is your method of success? I mean, it's luck, it's a lot of work, and I think a certain intellectual honesty to look at mistakes and admit mistakes, and then go over and do other things. I don't know.
Okay. A lot of work and a lot of luck.
Yes.
I think both you need
Yes.
to have. Okay, and a final question. Actually, it's two parts of this. In your opinion, what is the best way, I think it's related to the first, to develop fundamental research such as astrophysics and cosmology in Thailand, the country small like us? What is the fundamental, what is the way to do that? And the final part of that is, what is your own next step after you've discovered so many things, and what is your next step?
Well, if I could ask a question of the audience,
Yes.
I would ask the following. I tried very hard today to communicate some of the enthusiasm that I feel for research. Now, is anybody here, young man, woman, or whatever you, who felt that, who felt this enthusiasm, this interest, this joy in doing research? So I'm asking, I mean, raise your hands, or if you're too timid, don't, but I mean, is there anybody at all?
มีใครได้รับแรงกระตุ้นไหมครับจากการที่ได้รับฟังการปาฐกถาครั้งนี้นะฮะยกมือเลยครับเพราะเราอยากจะ
Well, I saw at least 2 people.
Oh, it's more.
More,
That's more,
fine.
that's more.
That's in excess of what I need. What I'm trying to say is these methods of taking people to come here and explain to you what they're doing in as simple a way as they are able to, which sometimes is difficult, that can communicate to some young people the interest, the ambition, the whatever, the desire to do research. So that's fundamental, because if nobody wants to do research, then you can throw in as much money as you want, but it will not be done. The second, so there should be people interested, culturally interested in doing this. The second thing is that between the government, the industry, the source of money in the country must provide for both basic and applied research. And I think the numbers are much larger than those that currently are being spent in Thailand. So that is required. And finally, I would say something which is a little unpopular, but I'll say it anyway. The research tends to be elitist. So you wish to concentrate on some things which you can do very well, and where you have bright people, and support them perhaps more than you would support other people. It's not a moral judgment, it's a statement that most of the research results occurred in somewhat elitist conditions. It doesn't mean in elitist academia, but in places, for instance, Bell Labs. I mean, I only have to mention that as an industry where an awful lot of discoveries were made. But they were concentrating on the best and brightest. And that is something which is very difficult for people to accept. For instance, in Europe, the universities themselves and the academic community has fought that, because they felt that the most important thing was to raise the general level of education rather than concentrate on elitist research. I personally think that even from the point of view of the general good, the concentration on elitist research has greater potential for for applied physics. That is, Shortley got the Nobel Prize because he developed the transistor, basically. But I don't have to explain that transistors were important to everybody. Towns for developing the laser. And that, this one didn't work so well, but okay, we all have it. So what I'm trying to say is that competitive, high-level, world-level research gives benefits. And hopefully, I mean, it's our duty, at least, to return back this privilege by working hard for the good of everybody. That would be my... And there are levels which I'll discuss tomorrow of research, percentages and so forth, but that's less important than this commitment and this understanding. Okay?
Okay.
Okay.
Okay, thank you. I think, unfortunately, we have very little time, and Professor will continue your discussion tomorrow at Triem Bodom School โรงเรียนเตรียมอุดมนะครับซึ่งมี Professor Giacconi จะไปมีสัมมนาต่อนะครับ Okay, before we conclude the program of this afternoon, in order to express our deepest gratitude, may I call upon the President, Professor Dr. Kunjing Suchada Kiranan, to present a souvenir on behalf of Chulalongkorn University as a token of our appreciation. Okay, today's lectures has come to an end, and I would like to express our deepest appreciation once again for the opportunity to learn about your expertise in astrophysics and X-ray detection. Please join me in giving Professor Giacconi a big round of applause once more. ท่านผู้มีเกียรติครับ การบรรยายพิเศษในวันนี้จบลงเพียงเท่านี้จุฬาลงกรณ์มหาวิทยาลัยหวังว่าท่านจะให้เกียรติมาร่วมกิจกรรมของเราอีกในอนาคตขอบคุณและสวัสดีครับ